Okay, let's start with a premise that it sounds simple, but it's actually incredibly difficult to pin down.
You're talking about the Turing test.
Exactly. Alan Turing, 1950. He basically proposed that if a machine can converse with you, so fluently that you can't even tell it's a machine.
Then we have to consider it intelligent.
Right, the imitation game. But here's the thing that always, always bugs me about it.
And what's that?
It only focuses on the output, on the conversation itself. It completely ignores the engine room. How is the machine actually doing it?
The answer has swung back and forth between two completely opposing philosophies.
A pendulum.
Yes, exactly. It's not just a steady march of progress. It's a pendulum.
Right, and that's what we're diving into today. The history of the machine that speaks. And honestly, looking at the research, this isn't just a story about code.
No, not at all.
It's a philosophical war between two camps. The rationalists, who think you have to teach a computer the rules of the world.
And the empiricists, who think you just need to feed it enough data to fake it.
Kenneth Church calls this the oscillation.
He does. Every 20 years or so, the field gets bored or frustrated with one approach and violently swings to the other.
So to understand why our modern AI works the way it does, we have to go back. Back to the first swing of that pendulum.
And surprisingly, it doesn't start with linguists.
No, it starts with a mathematician right after World War II.
Warren Weaver, July 1949. Weaver was a science administrator, and he writes this famous memorandum that really kicks off the entire field of machine translation.
But you have to get inside his mindset.
You do. He had just seen the Allies crack the Enigma code. For him, cryptography was like the ultimate tool.
So when he looked at a document in Russian, he didn't see a foreign language.
No. To Weaver, a Russian document was actually a document written in English.
It was just encrypted.
Exactly. Encrypted in a strange set of symbols called Russian. And he believed that if you could just find the logic of that code, you could decrypt it back into English.
Without knowing anything about Slavic grammar or Soviet culture.
Nothing.
That sounds incredibly arrogant, doesn't it? Reducing an entire language to a math problem.
It was naive, for sure. But it launched the first era of research. In the 1950s, the US, the UK, the USSR, they all poured money into this.
And they thought it would be simple. Just lexical substitution.
Which is just a fancy way of saying
Word-for-word swapping.
Yes, early pioneers like Richens and Booth built systems that were basically automated dictionaries. You feed in a Russian word, the machine looks up the English equivalent and prints it out.
But anyone who's tried learning a second language knows that fails almost immediately.
For instance,
I mean, there's that classic example. The spirit is willing, but the flesh is weak.
Right.
You swap that into Russian and back, word for word, and you get something like...
The vodka is good, but the meat is rotten.
Yeah, exactly.
And the researchers, they knew this was a problem. By 1955, Booth and Locke were already admitting that looking at words in isolation was a dead end.
They needed grammar.
They needed grammar. They needed syntax.
But they were still trapped by the hardware, weren't they? I was reading that the Soviet Union had this huge team working on it.
They did.
But they barely had any computers.
That's one of the most fascinating subplots here. In the late 50s, the USSR had more computational linguists than the rest of the world combined.
Wow.
But because they didn't have the computing power, they did thought experiments.
So human computers.
Exactly. They would literally sit in a room with a flowchart and a set of strict rules, and they'd have to translate text by following the algorithm mechanically without using their own intuition.
That must have been painstaking.
It was, but it forced them to be incredibly rigorous about the theory. It actually led to some brilliant theoretical linguistics. They were doing software engineering without the software.
But in the West, even with the computers, the results were underwhelming.
Very underwhelming.
And that brings us to the villain of this early era.
The ALPAC report.
Villain is a strong word, but...
For the researchers at the time, it definitely felt like an execution. In 1966, the U.S. National Academy of Sciences formed a committee, chaired by John R. Pierce, to see if all this machine translation investment was paying off.
And Pierce was a skeptic from the get-go.
He was a pragmatist. The committee looked at the output from these very expensive machines and compared it to a human translator. The machines were slow, they were inaccurate, they were expensive.
And the humans.
The humans were cheap and accurate. So the report concluded there was, and I'm quoting here, no immediate or predictable prospect of useful machine translation.
So they didn't just say, it's not working yet. They said, it's probably never going to work.
And that killed it. The funding just vanished. A nuclear winter for the field. But the reason they said it would fail is what's really important here.
Okay.
The LPAC committee believed that to translate a language, you have to understand the world.
Give me an example of that.
Okay, take a simple sentence. The box is in the pen.
All right. The box is in the pen.
To a human, pen here obviously means a playpen because a box can fit inside a playpen.
Right.
But if I say the ink is in the pen, now pen means a writing instrument. The word is the same, the grammar is identical.
But the meaning is totally different.
And the only way to translate that correctly is to have real-world knowledge about the physical properties of boxes and ink and pens.
And in 1966, computers knew absolutely nothing about the physical world.
Nothing. So the consensus became, we can't do translation until we solve artificial intelligence first. We need to build a mind before we can build a translator.
And this triggers the first big swing of that pendulum. We move out of the naive dictionary era.
And into the rationalist era of the 70s and 80s, the age of AI.
The field basically splits. Translation is dead in the water, so everyone pivots to natural language understanding, or NLU.
Right, and the goal now was to hand code the rules of the universe into the machine.
And the poster child for this was SHRDLU.
Terry Winograd's SHRDLU from MIT in 1972. It's iconic. It was a program that lived entirely inside a blocks world. Simulation.
A simulation of a table with colored blocks and pyramids and boxes. And you could type things like, pick up the big red block.
And it would actually do it.
It would do it. It seemed like magic. It could handle really complex commands like, find a block which is taller than the one you were holding and put it into the box.
It could figure out what the one referred to.
Yes, it could figure out pronouns and context.
But there was a catch, wasn't there? It wasn't really understanding language like we do.
No, because in SHRDLU's world, the language and the world were the same thing. The definition of the word block wasn't a dictionary entry. It was a piece of code that drew a square on the screen.
As pickup was just the name of the function that moved the little robot arm.
Exactly. It's called procedural semantics. It worked perfectly in the blocks world because the blocks world was the only thing it knew.
So if you asked it about the weather...
It would crash. It was a toy system. It couldn't scale.
Right.
But the researchers at the time thought, okay, we just need to make the world bigger. And that brings us to Roger Schenck and his idea of scripts.
I love this idea.
It feels so human, but also so rigid. The idea was that our lives just follow these predictable patterns.
Right. Schenck argued that we understand language because we have these preloaded scripts for common situations. The classic one is the restaurant script.
You go in, you wait to be seated, you order, you eat.
You pay, you leave, the whole sequence.
So if I tell the computer John ordered a steak and left a big tip, it can infer that John also ate the steak and paid the bill, even if I didn't explicitly say so.
Exactly, because those actions are part of the script. But just think about the effort involved. You have to manually hand code a script for everything. A script for a birthday party, for a doctor's visit, for a bank robbery.
And what happens if something isn't in the script?
The system breaks, it's brittle. There was this running joke that these AI systems knew a disturbing amount about interpersonal violence and dining in restaurants.
Because those were the only scripts anyone bothered to write.
But they couldn't understand a simple news story about an election.
So they were autistic savants for steak dinners.
In a way, yes. This was the absolute peak of rationalism, trying to teach the computer the logical rules of the world. But by the late 80s, it was obvious this wasn't going to scale.
You can't hand code reality.
It's just too messy.
So the pendulum is ready to swing again, and this time it swings hard. We're entering the 1990s and the statistical revolution.
This is the moment everything changes, and it's a total shift in philosophy. The field moves from rationalism, I will teach you the rules,
To empiricism. I'll give you data, you figure out the probabilities.
The engine room gets a complete overhaul, and the people leading this charge, they weren't linguists, they were engineers.
At IBM.
Specifically, a team led by Fred Jelinek. They looked at translation and said, forget grammar, forget meaning. This is a signal processing problem.
Explain that. How is language a signal?
They use something called the noisy channel model. It comes from information theory. Imagine I want to send you a message in English, but the telephone line is bad, it's noisy. By the time my message gets to you, the signal has been corrupted and scrambled into, let's say, French.
So they literally treated French as if it were just garbled English.
Precisely. Their goal was to build a mathematical model to decode the French back into the original pure English signal. They didn't care why a verb was conjugated a certain way. They just wanted the probability that word A in French came from word B in English.
But to calculate those probabilities, you need a ton of data, a massive amount of examples.
And that is where the Hansard corpus comes in. This was their secret weapon. The Hansard is the official record of the Canadian Parliament.
And by law, everything said has to be published in both English and French.
So you have a perfect Rosetta Stone, millions of sentences already aligned. The IBM team built algorithms that would just crawl through these sentence pairs and look for statistical patterns.
So it wasn't told that maison means house.
No. The computer just noticed that in 10,000 sentences containing the English word house, the French word maison appeared in the other version 9,800 times.
And it binds them together purely on statistics.
Yes. And it got incredibly complex, modeling word order and things like that, but always without a single linguistic rule. No subject-verb-object, no noun phrases, just math.
And this drove the linguists crazy.
They hated it. It felt like cheating. It was anti-intellectual. You had these brilliant people who have spent decades studying the deep structure of syntax.
And then these engineers come along, ignore all of it, and build a system that actually translates better.
Which leads to that infamous quote from Jelinek.
Every time I fire a linguist from the project, the performance of our system gets better.
It's ruthless.
But was he right?
At the time, he was. Every time they tried to force a linguistic rule onto the system, like adjectives must come before nouns, it actually made the translation worse. The statistical models were capturing subtle patterns that the rigid rules missed.
The data was smarter than the theory.
It was. But this shift wasn't just about clever math, it was about technology. Why the 90s? Three things: processing power, storage, and data. Moore's law finally caught up. And things like the CD-ROM made it possible to mail 650 megabytes of data around. And then the internet.
Suddenly, text wasn't something you had to type in. It was everywhere.
You could just scrape it.
So the empiricists won. The statisticians took over.
Completely. The 90s and 2000s were dominated by this approach. It wasn't just translation, it was everything. Sentiment analysis, for example.
Where a computer tells you if a movie review is good or bad.
Exactly. In the old AI days, you'd try to teach the computer the definition of good. In the statistical era, you just treat the review as a bag of words.
You don't read it, you just count.
You just count the tokens. If the word breathtaking shows up, the probability of it being a positive review goes up. If tedious appears, it goes down. It's pure correlation.
It's not reading, it's just looking for clues. But it worked.
It worked good enough. And that became the mantra of the 2000s. We stopped trying to build the perfect, intelligent machine like SHRDLU and accepted tools like Google Translate, which were messy but incredibly useful.
Which brings us to the climax of our timeline, 2011, IBM's Watson on Jeopardy.
Watson is so interesting because it represents a convergence. By 2011, the field had realized that pure statistics has its limits, but pure rules are too brittle. Watson was a hybrid.
It beat the best human players in the world. But how did it actually think? It wasn't just Googling the answers.
No, it was offline during the game. Watson used something called deep QA. It would take a clue, and instead of just looking for keywords, it would generate hundreds of possible hypotheses. It would parse the sentence to find the subject, the verb.
So it was using some of that old school grammar.
Yes! Then it would search its huge internal database encyclopedias, dictionaries, news archives. But the real magic wasn't in finding a possible answer. It was in knowing if it was the right one.
The confidence score.
Exactly. Watson would say, I found a strong link between architect and Paris, and the date matches. I am 85% confident the answer is Eiffel. If that confidence was below a certain line, it just wouldn't buzz in.
It was acting like an agent weighing evidence.
It was.
So if we look at this whole trajectory from Weaver's code breaking, which is empiricism,
to SHRDLU's rules, which is rationalism,
to IBM's pure statistics, back to empiricism, and then Watson's hybrid approach, where does that leave us now?
Well, if you look at the large language models we all use today, the GPTs of the world, we are currently in the deepest, most extreme valley of empiricism we have ever seen.
Because at their core, these models are just next word predictors, right? They're the IBM translation model on an unimaginable scale.
They are the ultimate noisy channel machines. They have ingested the entire internet, and all they do is calculate the probability of the next token based on billions of parameters. But, and this is the big question, do they know anything?
So if I ask a chatbot to explain quantum physics and it gives me a perfect coherent paragraph,
Did it understand the physics? Or did it just calculate that the word particle is statistically very likely to follow the phrase subatomic?
That is the debate. And this brings us right back to Kenneth Church's oscillation. He argues that we've swung so far into pure statistics that we're hitting a wall of diminishing returns.
You can keep feeding it more data, but you can't fix a fundamental lack of reasoning.
So are we due for a swing back? Is this the return of the linguists?
Church thinks so. He argues that students today need to learn the old rationalist methods, the grammar trees, the logic, because the next major breakthrough will likely come from combining the raw power of statistics with the structured reasoning of the 70s.
We might need to unfire those linguists after all.
Or at least go dig their textbooks out of the trash. We're already seeing this happen. Researchers are trying to teach chain of thought reasoning to LLMs.
Which is basically forcing a rationalist structure onto an empiricist brain.
Exactly.
It's fascinating. The future of AI might actually be buried in the so-called failures of its past.
That's often how science works. The blocks world was too small and too simple in 1972. But maybe, with today's computing power, we can finally build a blocks world that's as big and complex as the real world.
A machine that not only speaks, but actually knows what it's talking about.
That's the Holy Grail.
Well, this has been a huge tour. From the Cold War to Jeopardy! It really makes you rethink what's happening every time you ask your phone a question.
It's a lot more than just code. It's 60 years of intense argument.
Thanks for breaking it all down for us. And for you listening, I want to leave you with one final thought. If that pendulum really is swinging back toward reason and rules, what does that mean? Does it mean the next generation of AI will be less like a statistical parrot and more like, well, us? And if it is, are we ready for that conversation?
That's the deeper dive for next time.
Thanks for listening. We'll see you in the next deep dive.